So what we did in the first PowerPoint was we talked about torque, which causes things to rotate. Now we're going to talk a little bit more about the kinematics, or the equations of rotation. So that's what we're going to be doing now. So there's two basic types of fundamental motion: linear motion, where an object moves through space and time, and then rotational motion, which an object is rotating about some specific point. So that's what we're going to be doing. So the equations that you learned in the very first unit, like V equals delta x over t, we're going to be using those exact same equations. The only difference is they're going to describe rotational motion. It's really no big deal though. So we're going to, and they're in Greek letters, so they might look a little intimidating, but it's just the same equations that we learned first in the first unit. So instead of talking about displacement as delta x, we're going to have angular displacement, which is going to be delta theta. Okay, that's what that O with the line through the middle of it is. It's a theta. So we might move a meter, we might move through 2 pi radians. So we will be working with radians this unit. You do not need to set your calculators for radians. We're not going to be working with them like that. But we will be working with radians, so that'll be good. So that'd be torque with degrees, and anyway. So when we talk about angular displacement, we can say something makes one complete rotation. It rotates 360 degrees, or something makes 2 pi radians. So radians is the unit of choice that we want to be using when we're using the equations. We want to be in radians, basically. Okay, so this guy right here, we would say that moved half of a rotation, so that would be equal to pi radians. So here we've got 3 pi radians, or 3 pi radians. And here, if we go, what would the actual displacement be? Well, technically the displacement is 2 pi radians, because it backtracks a little bit on that. So okay, so when an object like a wheel is rolling along the road, it's doing both of the types of rotations at the same time. So it's rotating around and it's moving linearly. And of course it doesn't look like that. It's doing both at the same time. So so we can talk about linear rotation and linear motion and rotational motion all at once. Any idea how far a wheel moves, the center of a wheel moves as it makes one rotation on the ground? Well, what it did is, if you had a string laid around this, it would have laid out one circumference of string, because it made one rotation. So each time a wheel rotates, it travels through space and time a distance of one circumference. So that's what we just said. So a wheel on a bicycle travels 4 meters across the road. If the radius of the wheel is 0.25 meters, how many rotations did the tire make? So the first thing, we know that each time it travels one rotation, it's going to travel one circumference. So the first thing we want to do is figure out what the circumference is. So that's 2 pi r, so 1.57 meters. Okay, so that's 1.57 meters per each rotation. Okay, so if it travels 4 meters, we're going to divide that 4 meters by the 1.57 meters per rotation. Okay, and then meters is going to cancel out, rotations is going to flip to the top, and we're going to get 2.55 rotations. So, and you could just kind of logic your way through that one. So let's say we travel through theta radians. What linear distance does that point on the wheel travel? So we know if it traveled 2 pi radians, it would have gone 2 pi r meters. Okay, so let's start and use a little factor label to solve this. So theta radians. So every 2 pi radians, it travels one rotation. Okay, and each rotation, that point on the wheel travels a distance of 2 pi r meters. Okay, so one rotation cancels out. 2 pi cancels out, and that leaves r left over. So basically, canceling out with, why do I have the blue in blue? I don't know why I have the r in blue. The r shouldn't be in blue. The distance x something travels is equal to theta times r, because that's another thing that doesn't cancel out. X equals r theta. So if you travel theta radians, okay, you travel a linear distance of r theta. Thanks. So, and that'll be a recurring theme. Basically, the linear is equal to the rotational times the radius. Okay, you'll see that several different times. Whatever the rotational version of it is, if you multiply it by the r, you get the linear version of that. Okay, so angular displacement times r equals displacement, linear displacement. So, and there you just heard me use the term angular. Angular and rotational mean the same thing. We use them interchangeably. Just like moment and torque mean the same thing. I really don't use the term moment very much, but it is used pretty commonly in engineering. So here we've got velocity. So velocity equals average velocity equals displacement over time. Average angular velocity or rotational velocity equals angular displacement over time. Okay, so theta over t. So average velocity, average velocity. Look at tow-mater. My kids must have been in their cars phase when I was doing this PowerPoint. They were definitely for a while very much into cars. So other ways we could talk about rotational velocity or angular velocity, we could say radians per second, degrees per second, rotations per second, rotations per minute, and that kind of thing. The preferred way of discussing rotational motion is in radians per second. So that's kind of like the meters per second of rotation. So that's generally how we want to do it. So a wheel spins at 120 RPM. What is its rotational velocity in radians per second? So again, we want to take our RPMs and rotations per minute and convert that into the preferred method, which is radians per second, which is something that you'll be doing in the homework and probably on the test. So 120 rotations over minutes. Okay, we know one rotation equals 2 pi radians. So rotations cancels out, and we know 1 minute equals 60 seconds. So minutes cancels out. So we're in units of radians per second, and do the math and you get 12.6. So you should be able to convert between RPMs and radians per second. So just showing you where the next equation comes from. Since average velocity equals displacement over time, delta x over t, and x equals r theta, I can stick this in for x and get v bar equals r theta over t. Okay. And since theta over t equals average velocity, average rotational velocity, we get the equation that v equals r omega. Okay. If I haven't mentioned, this is a lowercase omega. Capital omega looks like a horseshoe. You've seen it with electricity if you took POE. So again, this is just kind of the reoccurring theme. If you take the rotational version of it and multiply it by the radius, you get the linear version of it. So rotational speed times radius equals linear speed. Okay. So again, but in order for this to work out, we got to be in our preferred unit, which is radians per second. Okay. So so to find the tangential velocity of something, it's equal to the angular velocity times the radial distance. So and this would be vt, the tangential velocity, just kind of connecting with the previous unit when we covered centripetal force and all that stuff. Okay. So so the same wheel is spinning at 120 RPMs or 12.6 radians per second. How fast is it rolling down the road if the diameter is 0.7 meters? Well, basically the edge of the wheel is spinning as fast as the road. So we basically just want to figure out how fast the edge of the wheel is spinning, which is the linear velocity. So if we know the rate angular velocity is 12.6, and we multiply that by the radius, so we'll find the tangential velocity or the linear velocity. So anyway, all we're doing is taking the rotational velocity, multiplying by the radius, and we get the tangential velocity, or how fast the wheel is actually rolling down the hill, which is 8.8 meters per second. Okay. So, and going back to the right-hand rule, so take your hand and follow. We can talk about the direction of angular speed, just like we talked about the direction of torque. It's the exact same right-hand rule. Curl your hands, look at that top picture, in the direction of rotation, and your thumb points straight up. Okay. Whereas if you curl your hand to follow that rotation in the bottom picture, your thumb points straight down, and that's the direction of the angular velocity vector. Okay. So so this guy right here, what would the direction of the angular velocity be for this guy? So if you curl your fingers in the direction of the rotation, okay, your thumb should be pointing into the page right here. And if you curl your fingers in the direction of this rotation, your thumb should be pointing out of the screen. Out of the screen. Okay. Next, we're going to be covering something like this. So what happened here is this guy spun up, meaning its angular velocity changed. Okay, it got faster. So what do you call something when its velocity changes? We call that acceleration. So that's the next thing, is angular acceleration. And again, there's just these are the exact same equations. Average velocity, or I'm sorry, average acceleration equals change in velocity over time. Angular acceleration equals change in angular velocity over time. It's the exact same equation, just with Greek letters. So this is a lowercase Greek alpha. I kind of draw it like a fish, and so same thing. So just to, again, try to connect the analogies here. If you look at the analog, so instead of x we use theta, instead of v we use omega, instead of a we use alpha. Average velocity equals displacement over time, same equation. Acceleration equals change in velocity over time, same equation. Just Greek letters. So here we've got a flywheel, and a flywheel is basically something that's spun and they store energy in that spinning. Cars have flywheels, or at least they used to. I don't know if they still do. Bikes don't really have flywheels. You consider your wheels your flywheels, I suppose. But anyway, so an experimental flywheel is used to store energy. Can reach speeds of 95,000 RPMs if they can charge in 15 minutes. What is the angular acceleration if the flywheel starts from rest? Okay, so we want to figure out the angular acceleration. So we're using we want to use the equation alpha equals omega 2 minus omega 1 over t. Okay, so we need to know the change in angular velocity divided by the time. Okay, we know our initial angular velocity is 0 because it starts from rest, and it says our final speed is 95,000 RPMs. Now we can't leave that in RPMs because we got to have it in radians per second. So we'll convert that into radians per second here. Multiply by 2 pi, divide by 60, and we get 9,948 radians per second. The time is in minutes. Convert to standard physics units, which means seconds. So we get 900 seconds. Okay. Use the equation finally. Now that we got everything in the right units. So omega 2 minus omega 1, 994. I don't know why I have 8 here and 5 here. Just go with it. 9948 minus 0 over 900 gives me an angular acceleration of 11.1 radians per second squared. So this is just a matter of using a familiar equation, having to convert the units, having to convert units on it. No big deal. Okay. So so again, I wanted to make another connection, reinforce another connection with you. Remember how I said you take the angular, you multiply by the radius, and you get the linear. Okay, that's what we're just trying to illustrate here. Okay. Angular displacement times radius equals linear displacement. Angular speed times rotation times radius equals regular speed. Okay. Angular acceleration times radius equals linear acceleration, etc. Okay. So a car has wheels with a diameter of 80 centimeters and is initially traveling at 14 meters per second. If it comes to a stop in 2 seconds, what is the angular acceleration of one of its wheels? Okay. So we've got the diameter, which we'd have to convert to radius, so in meters, so 0.4 meters. So that's no big deal. We've got the initial speed is linear speed v is equal to 14 meters per second. Okay, and it comes to a stop in 2 seconds, so we know the time, and we're looking for alpha. Okay. So alpha is the final angular velocity minus the initial angular velocity divided by the time. So I know the final angular velocity is 0 because it says it comes to a stop. Okay, I'm going to need to know the initial angular velocity, but all I know is the linear speed. Remember the previous slide? If I'm going to go between the linear and the angular quantity, I just use the radius. So it's linear equals radius times angular. Okay. So our linear is equal to 14, radius is 0.4 times omega. So my initial angular speed is 35 radians per second. So I plug that into my acceleration equation, and we get 0 minus 35 divided by 2, and we get the angular acceleration is equal to negative 17.5 radians per second. Okay. So this is kind of a lot to throw at you, but you've seen all of this before. I'm just wanting you to see that for every equation that I gave you in Unit 1, there's a rotational equation that works, so you can use that. Okay. If you don't feel comfortable, you can convert it to linear, okay, and then do your equations in linear, okay, and then convert back, I suppose. But all these equations should hopefully look familiar, and you know, this is not something I'm going to make you memorize, although you should probably have these more or less memorized by now. Probably a little review, maybe it might be in order, but you know, the ones that aren't on the equation sheet you probably know. And so, and to go between these, you use these two equations. So and there's the x equals r theta too, that equation. Okay, let's work a problem that uses one of these equations, just so you can kind of see how it works. So let's work using those equations. So we've got a wheel radius r equals 0.25 meters. The wheel is initially rotating at 23 radians per second, so we've got omega 1. And accelerates at 5 radians per second squared, so that's my angular acceleration, so we've got alpha. For 8 seconds, so we've got t. So equation, or the first part of the problem is, what is the final angular velocity of the wheel? What is the angular displacement of the wheel? And how far did the wheel travel? Okay, so in F, what does the speedometer in the car read after the 8 seconds? My mouse is malfunctioning. So the first thing we want to do is list out our knowns. So we've got omega 1, as we said, alpha, and t, and we're looking for omega 2. So this is the same equation as v2 equals v1 plus at. We're just using it in the rotational form. So we're looking for omega 2, so we plug in 23 for our initial angular velocity. Our acceleration is 5, and our time is 8. And we get our omega 2 is equal to 63 radians per second. Okay, so part B, what's the angular displacement? So we can use our version of delta x equals v1t plus at squared over 2. Okay, so that equation hopefully looks familiar. And so we plug in the numbers, and we get 344 radians. So again, the equation that we're using here is delta x equals v1t plus at squared over 2. That guy. We're just using it and the rotational form. See how far did, what was it asking? How far did the car travel? So now here we're looking for linear distance. Okay, so x equals r theta. So take the angular and multiply by the radius, and you get the linear. So 0.25 times 344, which we just found, we get 86 meters. And lastly, what does the car speedometer read? So we're looking for linear speed. In A, we figured out the rotational speed. So we're just going to do multiply by the radius and convert that to linear speed, and we get 15.75 meters per second. Now I know not many car speedometers read out in meters per second, but just bear with me. Okay. One more problem, and that is where we're going to stop for the day. So we've got a human centrifuge they use to spin astronauts and test how many G's they can take. Takes 1 minute from rest to make 20 complete revolutions, at which point it reaches its final speed. What is the angular acceleration and its final angular speed? So we've got an initial velocity of 0, so omega 1 equals 0. T is equal to 1 minute or 60 seconds. The angular displacement, it gives us in rotations or revolutions, but we need to have that in radians, so convert to radians, multiply by 2 pi, and we get 125.7 radians. And the first question is, what is the angular acceleration? So there's more than one way to attack this problem. The most direct way is to use delta x equals v1t plus at squared over 2. Okay, that equation, and just stick in the rotational components. So the angular displacement is 125.7. My initial velocity was 0, so that goes to 0. And we're looking for alpha, and t is 60, square that, divide by 2. And we get 0.0698 radians per second squared. So that is A. The next question is, what is its final angular speed? Again, more than one way to do this. I just used omega 2 equals omega 1 plus at, or v2 equals v1 plus at, if that sounds more familiar to you. And we use the acceleration that we just found. Our initial velocity is 0, and our time is 60 seconds. So the rotational speed is 4.19 radians per second. So hopefully you're able to make some connections with what we've learned before, and this doesn't freak you out too much. So it's really not that bad, although I could certainly understand being a little leery at first. But hopefully you'll do just fine with this.